Number 14 then, from the 2014 Advanced Higher, take 2. I'll explain in a minute. Well, how does it start off by saying? Given this series, write down the sum to infinity when the absolute value of r is less than 1. And it would have to be, if you've got an infinite series, the only way it could converge to a limit would be if the terms got smaller and smaller. In other words, if r was a proper fraction. The other test is, if you divide consecutive terms, then the limit of that, for the big terms as n goes to infinity, the limit of that ratio should also be less than 1. Obviously, dividing the terms also produces r as less than 1. Still, you should recognise this as a geometric series, where the first term is 1, and the common ratio, I'll have to use a different letter then, I'll circle that to stand for the variable ratio, the common ratio is r. And if that's the case, the sum to infinity is a over 1 minus whatever the common ratio is. So in this case, the sum to infinity will be 1 over 1 minus r. It then says, obtain an infinite geometric series for 1 over 2 minus 3r. Well, it must be that originally you took a geometric series and got the sum to infinity. So this time you must be regarding this as the sum to infinity and rearrange this to get back to an original geometric series. Now this is where take 2 comes in. I originally rearranged that by splitting the terms to put it into this form and got a geometric series, but I got a comment from my very favourite videos, that's a YouTube channel, saying that he had taken a common factor out and got simpler results, and that is exactly correct, because the way I did it, I created an infinite series with a different centre of convergence. Now, it doesn't matter what that means, I think he knows what it means. So, for this part, how can I make this look like this? Well, if you take a common factor of, if you take a factor of 2 out of the denominator, you'll be left with 1 minus 3r upon 2. Rewriting that as a half on top over 1 minus, and just emphasising this part, 3r upon 2. That would be the sum to infinity of a geometric series. That's the sum to infinity of a geometric series with a equals a half and r, I'll just put it that way, equals 3r upon 2. So that 1 over 2 minus 3r can be written as this geometric series, starting with a half and then multiplying by 3r upon 2, so that the next term would be 3r upon 4. It would be better to write that as 3/4 of r. The next term would be 9r upon 8 squared, then multiplying by 3 upon 2 again, then 27 upon 16r cubed, and so on. So there's the geometric series. And the second bit said, for what values of r is this series valid? Well, valid means converge. That will converge for, I've not left myself a lot of room, I'll just put it over here. It will converge for r is less than 1, where r of course means the common ratio. So this will converge for 3r upon 2 is less than 1. Right, there's two parts to that. You could say 3r upon 2 has to be less than 1, in which case r is less than 2/3. And the other half is 3r upon 2 has to be greater than -1, which means that r is greater than -2/3. So the second bit for this is, it's equal to that, and it converges for r is less than 2/3, greater than -2/3. Part B then. Express this in partial fractions. Well, the first step would be to factorise the denominator. It must factorise, or else you'd just be stuck with that. And if it does, it can only be 3r times r, and a 1 times a 2. Same signs making a 5, we'll put the 2 there, and they're both going to be negative. That's what you're going to change into partial fractions. So you can have a over 3r minus 2 and b over r minus 1. well, multiplying by the denominator, I'd have a times r minus 1 plus b times 3r minus 2 equals 1. Now some knockout values will do nicely here. R equals 1 knocks out that, leaving you with 3 minus 2 is just quite handily. B equals 1. R equals 2/3. Means that I've got a nastier 2/3 minus 1, which is negative 1/3 of a equals 1, which means that a equals negative 3. So that this can be written as negative 3 over 3r minus 2 plus 1 over r minus 1. However, it does say determine the first three terms of an infinite, not a geometric, an infinite series for this. So this must be obviously something to do with the first part. And those two things should really ring a bell. And look, they're the wrong way round. That's easily taken care of. Use that negative to reverse that denominator. 3 over 2 minus 3r, ding ding, and change that to a negative so you can reverse that denominator. There you go, there's the other one. So when it says rewrite this as an infinite series, the first three terms of an infinite series, if that's the sum of that infinite series, and those are the two parts that make up this, then I simply need to break them back down into their infinite series, but only the first three terms of each. Now that's just a slight rearrangement of the first one. Because remember, in the first one you had 1 over 2 minus 3r was rearranged into a half of 1 minus 3r upon 2. This time I've got 3 times it, so it'll just be 3 upon 2 times it. Maybe I'll just mention that here. That's 3 upon 2 over 1 minus 3r upon 2 minus 1 over 1 minus r. Two geometric series. This one's slightly different this time. So if it wants the first three terms, I'll just subtract them. Maybe I'll just take this bit away. There we go. So what are the first three terms? Well, this time a is 3 upon 2. And the common ratio is 3r upon 2, so it'll be plus, and then multiplying by 3 upon 2r, that'll be 9 upon 4r. Multiplying by 3 upon 2r again will be 27 upon 8r squared. And it would go on, but we only want the first three terms. And this one's simpler. First term 1 and common ratio r, so that's just 1 plus r squared. Should have indicated where I decided to stop the part on partial fractions. Maybe I'll stop it here as my answer for the partial fractions, then continue here for the further part of the question. So let's put the two parts together. We've got 3 upon 2 minus 1 is a half. 9 upon 4 minus 1 will be 4 away as 5 upon 4 r. 27 upon 8 minus 8 would be 19 upon 8 r squared, and I'll put plus dot dot dot. Those would be the first three terms. And we'll just stick it again over here. 1 over 3r squared minus 5r plus 2 should come to that. Now the last part says, for what values of r does the series converge? Well, the first step is, this isn't a geometric series. There's no common ratio there. 5 over 4 divided by a half is not the same as 19 over 8 divided by 5 upon 4. So you can't try and rearrange this into the form of 1 over 1 minus and hope to find the common ratio that you're going to use. But if this series is to converge, both of those would have to converge, which means that the convergence would have to apply to both of them, so you should be looking for the values of r that makes both of them converge. Now this one converged for r is less than 2/3 greater than negative 2/3. This one converged for r is less than 1 greater than negative 1. The only values of r that satisfy them both is r is less than 2/3 greater than negative 2/3. So we'll put that down. Converges for r is less than 2/3 greater than negative 2/3. Now I can check that by using the ratio test for convergence, but I'll need to clear this space. Putting that up here then, in the original form before it was gathered together, because I'll need to have the formulas for each term to use the ratio test. So what would the formula be for each term in terms of the term position, n, so n going from 0 to infinity? Well, there's two parts to it. For this part, just take this general term here. So if that was r to the n, there's going to be one more factor of 3 upon 2 multiplying it. So that would be 3 upon 2 to the power n plus 1. And this one, and the corresponding term, would take away r to the n. So putting that together, you have 3 upon 2 to the power n plus 1 minus just 1, lots of r to the n. There's your power series. Now, when does it converge? It'll converge when un plus 1 over un is less than 1. So what would that fraction be? Well, the next term, n plus 1, would have, in this case, 3 upon 2 n plus 2 minus 1 multiplying it. The bottom would be just n, just the way it is just now. 3 upon 2 n plus 1 minus 1. There's the ratio of the following term divided by the previous term, and the limit of that as n tends to infinity should be less than 1 for it to converge. That's the ratio test. Now it's just a case of what do you do with this? Well, before you can let n go to infinity, you don't want any of these n powers sitting on top. You want n's underneath, and then you know that that whole thing will go to 0. So, well, the first bit is this bit's quite simple, because I'll just be left with one r on top, so there's an r there. The way to get rid of this term is to divide by it. If you divide all the terms in this fraction here, that's multiplying, by divide by 3 upon 2 to the power n plus 2, then what would you have? This divided by 3 upon 2 to n plus 2 would be 1. 1 divided by that would be 1 over 3 upon 2 to the power n plus 2, multiplying it. Similar at the bottom would be minus 1 over 3 upon 2 n plus 2. But this term, n plus 1 divided by n plus 2, means you've still got one of them underneath. You've got 3 over 2 left underneath. That's what you've got to be less than 1. Begin to run out of space here as n tends to infinity. And when you tidy that lot up, when you let that go to infinity, this term disappears, this term disappears. That would then come over to the top and make 3 upon 2. So you end up with 3 upon 2r has to be less than 1. Then as before, r is going to be less than 2/3 or greater than negative 2/3. r is less than 2/3 or greater than negative 2/3. So I'm not sure if for this last part, because there are 6 marks for this, whether you're meant to go through this ratio test to get the values of r for which it converges, or simply make the statement I said originally. There is another way. So putting it back up here again, only this time in the original form, that was the answer with an extra term to the question before it says what's the values of r. There's something else you can do. If I just take this, which was the sum, and call that the sum, and multiply that by r, so I've got r times the sum, I would have a half r plus, what's a 5 upon 4 r squared, plus 19 over 18 r cubed. And if I then do the top take away the bottom, 1 minus r times s, I would have a half plus 5 upon 4 take away a half would be take away 2, which is 3 upon 4r, r squared. 19 upon 8 take away 10 upon 8, that becomes 9 upon 8 r squared. It's getting a bit trickier. 65 take away 38 is 27 upon 16 r cubed. And of course what we've got here is a geometric series. That would be a geometric series which would then just go to first term a half, common ratio has been multiplied by 3 upon 2, so minus 3r upon 2. It would go to that if this thing, 3r upon 2, was less than 1. So there's the same answer. R is less than 2/3 greater than negative 2/3. Notice if you were to take that a step further, S would then be a half over 1 minus 3r over 2 times, dividing by that 1 over r. Take that 2 down to multiply the bottom, 2 minus 3r times 1 over 1 minus r. 1 over, reverse the signs by multiplying a negative times a negative here, 3r minus 2 times r minus 1, which was of course your original expression. But does that not just imply very simply then that if S is equal to that, which remember factorised to 3r minus 2 times r minus 1, and that can be rearranged just by flipping the signs in both of them, which will keep it the same, 2 minus 3r 1 minus r, that I could then just take that across and multiply it to have this, and then say, well, this is a sum. Remember, 1 minus r is just a number. That's just a number multiplying a sum. And if that sum exists, if it converges and exists, then this will just be some number times some finite number. That will be a finite number as long as this is a finite number. This representing that sum to infinity of a geometric series. And that exists so long as 3 upon 2r is less than 1, negative 2/3 to 2/3. However, this says, because it was down below, r cannot equal 1. Well, that doesn't clash with this. But if you can do that, can you not also do, well, that means 2 minus 3r times s should be 1 over 1 minus r. And then you would say the same thing again. If this converges to the same value as this, then when does this converge? This converges for r is less than 1. However, that means it could be between 1 and negative 1. However, this part here says r can't be 2/3. So 2/3 is actually within this range here, which means this arrangement can't apply. But is that not just the same thing then as saying the very first statement, the range that applies will be the smaller one, the one that's contained within the other one, the intersection of the two. In other words, if you had to choose between negative 1 to 1 and negative 2/3 to 2 to 2/3, that's the one that would apply because that satisfies them both. Nasty stuff, convergence.